Hi everyone, my name is Miroslav Tushev and I'm a PhD student in the Division of Computer Science and Engineering at Louisiana State University. Today I'll be presenting a paper, Linguistic Documentation of Software History. In this paper, using a dataset of 32 open source projects sampled from 4 programming languages, we explore how project maintenance activities impact code lexicon. We found that the effect differs from language to language and from project to project. New features come with new vocabulary, which lead to higher rate of change in code lexicon. This can affect project stability, therefore optimal levels of linguistic change need to be defined to keep projects stable and at the same time to not restrain developers' productivity and creativity. We all know that source code has two components, semantics and syntax. Semantics is the meaning of the code. It denotes what the program does. Syntax is the form or structure of expressions, statements, or program units. In this example, these two functions are semantically equivalent, but syntactically different. The difference comes from the developer-defined language, or lexicon. It is not clear from the first example what is going on in the code, but example 2 makes it clear by providing meaningful identifier names. Identifier names are very effective at capturing the understanding of code by mature developers and newcomers alike. In the context of software systems, code lexicon is shaped by developer activities. We identify 3 main categories of activities: bug fixes, feature additions, and improvements. These activities have a significant impact on software vocabulary, thus on developers' ability to understand the code. Project history expressed through lexicon change can uncover valuable history events that led to that change, revealing aspects of a system that are typically overlooked by existing version control systems methods, such as diff or abstract syntax trees. In this paper, we study code evolution through the lens of developers' language, code lexicon. Our objective is to quantify the impact of different types of maintenance on code lexicon, and our motivation is to lay out preliminary foundation for modeling linguistic history of software systems. For our data collection process, we identified 32 open source projects on GitHub, sampled from 4 programming languages: Java, C#, Python, and JavaScript. Our main criteria for selecting those projects were popularity, expressed through the number of stars, long maintenance history with large number of releases, and explicitly classified maintenance activities for each release. This decision was made in order to ensure the validity of our results, because it can be challenging to accurately classify the types of maintenance activities based on commits alone. For example, here is one of the projects in our dataset, NewPipe. Every release of this project contained information on what new features had been added, improvements made, and bugs fixed. For this particular release, 1 feature, 2 improvements, and 5 bug fixes were implemented. We counted individual maintenance activities for each release and for each project. For every project in our dataset, its releases were downloaded and lexicon was extracted. To extract the lexicon, we relied on regular expressions rather than abstract syntax trees, because for regular expressions, code does not have to be complete or be able to compile. Code lexicon consists of all words used in the source code except for programming language specific keywords. Stop words were removed as well. All resulted code identifiers were split into their constituent words and stemmed in order to reduce the words into their morphological groups. To quantify the magnitude of linguistic change between 2 releases, we relied on Peterson's word frequency model. In particular, every ith release lexicon was compared with every jth release in the following way: the number of different words between the 2 releases divided by the number of unique words in both releases, where I and j are 2 consecutive releases. The linguistic change between I and j releases was then compared against the number of bug fixes, feature additions, and improvements for release j. As an example, here is how it would look like for Synapse project. On the x-axis, we have consecutive releases, and on the y-axis, we overlap linguistic change and maintenance activities for each release. We can see that the peaks for the linguistic change line coincide with the spikes in maintenance activities. To find out whether specific maintenance activities can predict linguistic change over release, we use Granger's causality. Granger's causality is a technique that is used to test if one variable precedes another in a stationary time series. In this example, the values of A are able to predict the values of B with almost perfect accuracy, which is visible at the peaks of individual plots. The number of time units between the peaks is called lag. In this example, lag equals 1. In our analysis, a lag of 1 means one release apart. We used 3 values of lag, 1, 2, and 5. The results show that feature additions were the most significant predictors of linguistic change, followed by improvements and bug fixes, which were able to significantly predict linguistic change in a smaller number of projects. We also noticed the differences between different programming languages. For instance, bug fixes significantly predict linguistic change for 5 out of 8 C# projects. For Python projects, feature additions and improvements cause the most disturbance in code lexicon. In contrast, JavaScript projects showed significantly less linguistic sensitivity to feature additions and improvements. For the majority of the projects where lag of 1 is significant, the lags of 2 and 5 are also significant, which suggests that bug fixes, feature additions, and improvements have a long-term impact on linguistic change and are not limited by a single release. We represent the expected impact of our work using soft goal interdependency graphs. Our ultimate challenge here is to be able to build a theory that uncovers best practices for building and maintaining vibrant open source communities and fostering innovation in open source development teams. For instance, creativity is often defined as a function of new features proposed and implemented. Our analysis showed that new features came with new vocabulary, thus more linguistic change. However, higher levels of linguistic change might destabilize the project. In open source environments, project stability is a necessity for quality control. Therefore, resolving the interdependency relations between linguistic change, creativity, and quality can help to define the levels of linguistic change that can be optimal for keeping the system's quality under control. At the same time, do not restrain open source developers' creativity. Thank you for your attention. I'm looking forward to your questions.